we're studying patterns and nonlinear functions, and this is part 2 of the video. In the first part of the video, we looked at this situation with the blocks, and when we had our graph, we had y equals x to the third power. We talked about how this graph would look. We talked about how the graph would not actually go past the y-axis, because in a real-life situation of this, we'd have a coordinate point at 0, 0, because if there were 0 blocks, edges, there'd be 0 blocks in the entire figure. This does not mean that this graph does not keep going in a non-real-life situation. Okay? When we have y equals x to the third power. When we have x, the variable being the base, and 3, a cube situation, we're actually going to have an asymptote graph, where this is going to kind of be mirrored. What we had in quadrant 1 will be mirrored into quadrant 3. Okay, and that's kind of how the shape of the graph would look. But that's not the same as a different situation. Okay? Here we see the table shows that the number of new branches in each figure of the pattern. What is the pattern you can use to complete this table? So, we look at this, we have figure 1 right here. The black part of this is the set starting point. Okay, that's almost like your step 0 would just be that black line. And each time we add 3 branches off of each new part. So 1, 2, 3. And as you can see, here were the 3 branches we added. And then off of those we added 1, 2, 3 each time. Okay, and so on as the pattern keeps growing. Alright? So number of figures, right? We have 1. There were 3 new branches. 2, we added 9 new branches. 3, we counted all these red lines over here, these red branches, we'd have 27 total. We need to figure out how this is growing from step to step in the pattern, right? So we looked at like common differences as one of the things, right? This would be a difference of 6. This is a difference of 18, okay? So there's no common difference. And last time we recognized that if you were raising, some number to that power, right, to the third power, it would work. But I don't think if we raised 1 to any power, we would get 3, 2 to any power, we would get 9. Okay, it wouldn't be the same thing for the whole table. But sometimes there's a common ratio, okay? I can get from 3 to 9 by multiplying by 3. I can get from 9 to 27 by multiplying by 3. Okay, and this will end up being true for the rest of the table. If I multiply 27 times 3, I get 81. If I multiply 81 times 3, I get 243. When you see a common ratio like this, you can figure out the function rule, even though this is going to be a nonlinear function. Right? We know it's nonlinear because there's not a constant change in the graph. There's a common ratio, not a common difference, right? As we're going up each time or down each time. That's that rate. When it's a common ratio, you can have a special type of an equation. Okay? We end up with these coordinate points: 1, 3, 2, 9, 3, 27, 4, 81, 5, 243. All right, and we can start to see the connection between those numbers. All right? We take 3 and raise it to an unknown power. We can get to this. These ordered pairs. If I raise 3 to the first power, I end up with 3. If I raise 3 to the second power, I end up with 9. If I raise 3 to the third power, 27. 3 to the fourth power, 81. 3 to the fifth power, 243. So when there's a common ratio, the common ratio is the base, okay? And your exponent is going to be the variable. It's going to be your input in the function rule. Your output would obviously be the numbers that you're getting. Okay, so our graph would look like this. Now, last time we said that at 0, we would have no blocks, and that was true. But here, we'd have the one piece. We'd have that initial black line. And that's evident with the y equals 3 to the x power. Any non-zero number raised to the 0 power is 1. So we have a coordinate point at 0, 1 right here. So your graph isn't going to go through the origin. And we can kind of see that graph. Now this graph is going to be different than the last one. It's not going to be an asymptote. It's not going to kind of flip and mirror itself into the third quadrant. Okay? If we start to substitute in negative numbers here, all right, so again it was y equals 3 to the x power. 3 to the negative first power, we're thinking of that as 1 over 3 to the first power, which is just 1/3. If we raise it to the negative second power, we're going to have 1 over 3 squared, which is 1/9. Negative 3, all right, if we have 3 to the negative third power, that's going to be 1 over 27. Okay, and you'll see it's these same numbers, they're just going to be under 1. This graph is actually going to keep extending, almost looking like a straight line, although it's not. And it's going to infinitely get closer to 0 without ever reaching 0. This would be an exponential graph.